The next thing is waves are of two major types. The first type of waves, we can call them electromagnetic, and then we have the mechanical waves. There are two types. So now let's look at them. So electromagnetic waves, first of all are transverse, then they all travel at 3.0 into 10 raised to 8 meters per second in air or vacuum. Since they can travel in vacuum, they do not require a medium. And then these electromagnetic waves are like radio, infrared, light, etc. So these are some examples. Okay, we're gonna study them separately as well. Now comes mechanical waves. Mechanical waves can be transverse or longitudinal. Write that please. Now they cannot travel in vacuum, and the reason why they cannot travel in vacuum is that they require a medium. Medium means solid, liquid, or a gas. Okay. Now, some examples of these can be like water, seismic, sound, etc. So these are type of waves which require medium, right? So you can write this down, please. All right. Furkan, please come on time, okay? Okay, now kids. So the next thing I'm gonna basically learn is what do we mean by transverse waves and longitudinal waves. So longitudinal waves are waves those oscillate perpendicular. So this is basically the keyword, okay? Perpendicular to the energy propagation. Propagation, you can also write it, you can also write transfer, that's fine. This is the keyword, right? So perpendicular is the keyword. I'm gonna highlight that so you guys do not forget about this. Then, commonly, these are light, water, waves, and seismic S wave. Seismic basically means earthquake waves, by the way, like that. And what they do is they basically go like this. So they oscillate up and down, and the energy is transferred perpendicular to it. So you can draw this place.
Sir, can we send seismic waves underground through a long distance?
Yes, it can come through a very long distance.
Oh.
That's why earthquake sometimes comes in like another country, and then you can also feel the tremor. Okay.
Yes.
Then basically comes longitudinal waves. These are waves. Those oscillate parallel to. So the parallel is the keyword in this. Parallel to energy propagation. Again, I'm telling you, this is the keyword. You can change other words like you can write wave, those oscillate or vibrate or propagate energy or transfer energy, but do not forget to write parallel. Okay, this is the most important thing. So then the examples of longitudinal wave, you can sound is a longitudinal wave. You can also make them. You can also display them through slinky spring, and also seismic D waves. So basically, they look like this. They have regions which are closer, and then regions which are further away from each other. it would go back and forth. So this is basically the oscillation, and then that's energy that is being transferred like that. Is it clear?
Yeah.
Yeah. So please draw this as well. Cool. Should I go forward then?
Yes.
Now, when you basically represent waves, okay, so waves can be represented by two different waveforms. For example, one waveform is that you can basically draw them with respect to displacement on the y-axis and distance on the x-axis. Or you can also do the same, but then you can draw it with respect to time in seconds. Now, so when you draw a wave like this, so the top parts of the waves, which are these are called crests, and the bottom parts of the waves are called trough. Again, the same crest, crest, trough, and trough like that. Now, the first thing we can do by looking at these graphs, we can find the wavelength. Now, please write the definition for wavelength. So, wavelength is basically distance between two successive points in phase. Now, this definition has a keyword as well, which is successive, which you should not forget ever. Now, most of you do not know what in phase means, but we're gonna basically learn that in a bit. Right now, just write this definition. So the SI units for wavelength are meters. The SI units of wavelength are meters, and the symbol that we use is lambda, like that. It's called lambda. And just remember, this is a scalar quantity, so it doesn't have a particular direction. So how do you do this? You go on the wave, and if you find the distance between the crests, one crest to the next, this would be 1 lambda. The distance between a trough and a trough is also 1 lambda. And if you take the whole portion of the crest or whole portion of drop, you include that, this would also give you 1 lambda. Is it clear, everyone? Yes, Shazib, Abdullah, Dania, everything is clear?
Yes.
Let me know, okay? Now, after that, we find amplitude on this one. How do you do this? Amplitude is the maximum displacement of a wave from mean amplitude.
So you're lagging for me. Is it only me?
I don't know. Am I lagging for everybody else too?
Yes. Yes.
Yes, sir.
Okay. Wait a second. I'll be back. I'll be back. You guys can copy this. I'll be back. All right. Please Second. No, which all right. I think it will be fine now. So you guys can hear me now? Is it okay?
Yes.
So I was saying basically the amplitude is the maximum displacement from the mean position. I just want to tell you that this middle line is the mean line. Mean line means it's the middle of or average of both sides. Okay. So you can find the amplitude by either going up till the crest, or you can go down till the trough. That would also give you the amplitude. Okay. Then,
Sir, could we say that's the equilibrium?
yeah, mean position is also equilibrium. That is correct. You're right. Then comes just displacement. They're sometimes going to ask you this definition. So if they say just displacement, you're going to say the displacement of a particle on a wave is its distance from equilibrium in a specified direction. Generally, they're going to give you, you use the symbol for displacement as y. They can also call it x, and the SI units are the same as meters. So basically, it's like this. So at any point from the mean position, if you go, so that would be displacement. So displacement means any point other than maximum displacement, which is called amplitude. Is it clear, everyone? So you can basically
Yes.
write this, please, and then you're going to go forward.
Done, sir.
Okay, good. So the next thing we're going to go towards is the time period. Now, time period is defined as time taken to produce one complete wave. That's time period. The symbol for time period is capital T. The SI units for time period are seconds, and it is a scalar quantity. So to find the time period, what you need is you need a wave that has time on the x-axis. So then you can go from crest to crest. That is a time period. You can also go from trough to trough. That would be the time period. And you can basically take one whole crest, one whole trough. That would also give you the time period like this. So yeah. So you guys can now write this down, please. Okay, now let's go to the next. So then we're going to look at the frequency. Now, how do you define frequency? Is number of waves produced in 1 second would define frequency. The symbol for frequency is F. The SI units for frequency are Hertz, which is Hz, and it is also a scalar quantity, by the way. So then, after frequency, we can actually then find the wave equation. Now, wave equation derivation is included in our course. So it's a very small one. It will come for just 1 mark, but then we should know. So we're going to say speed equals to distance over time, right? So this is what we know. For wave speed, one whole distance is the wavelength, and the time that it takes to produce one wave is the time period. Now, since frequency is equal to 1 upon time period, so I did not write it, sorry. That's how frequency is found. Also, by the way, frequency can also be written as 1 upon second. So, since frequency is 1 upon time period, so V can be written as F lambda. So this is the equation that we have studied before in IG as well. And this is the same here. You just need to learn the derivation of this. And that would be all. Okay?
Sir, can you mark
Exactly.
frequency on the graph?
Do I mind what? Sorry?
Can you please mark frequency on the graph? Because I get confused with
Frequency cannot be found from the graph. You have to find the time period and then divide the time period. You can divide 1 by the time period to find the frequency. Okay?
Okay.
Frequency just has a formula. This is the time period that you can take it from the graph, and this is the frequency value. Is it clear?
Thank you.
Yes. Okay. All right, Zirwa, how's it going? You get everything? And Shazeb, Asma, Farina, Fatma.
Yes, sir.
So this was all from obviously IG. Now we will be going towards the real thing, okay? And yeah, the first topic from A levels is called understanding phase and phase difference. Now, in the definition of wavelength, I wrote that wavelength is basically the distance between two successive points in phase. When I say phase, phases in simplistic words, I can explain that phase means it's just a position. Okay. For example, if I draw a circle here, and along with this circle, I want to draw basically a wave. So this will be the displacement. And here I will draw angle theta. Okay. So when the wave was at this point, let's call this A, which means currently its displacement is 0. It's just here. Do you guys understand that?
Yes.
So
Sir,
if you move, yes,
why is it a circle? Why are we taking a circle?
because circle represents a whole oscillation as well. All right, we're just comparing it. You'll see at the end. Huh? Huh? Yeah. So if you go from A to B, so what is the angle you would basically move? That's 90 degrees, no? So that means at 90 degree, if it's 0 degrees, so at 90 degrees, you will have the maximum displacement. So it is going to look like this. You get it?
So why is the displacement 0 when the angle is 0?
You can see, you see right in front of it, it's just 0. When it
Oh,
went
okay.
to 90, it got here. Do you get it? So I'm just comparing it. Side by side, I'm doing it. Is it clear? Now, if I further move to point C, so how much angle would I go through? Now, 90 more, which is 180, right? And the
0.
displacement again will be 0. Yeah. So it's gonna look like this. Get it? So this will be your 180 degrees. Then, if I go further down, I'm moving like this again. So I have to go through 90 again. So what is the total angle I've moved? 270. Now see the displacement is right here. So it's basically like this. And then if I go back to A again after D, so I have to move a total angle of 360 to go back into the same position. So it will look like this. So it's sort of basically you can see a wave is forming. So one whole oscillation is also equal to one whole wave. Do you get it?
Yes.
So we can conclude from this diagram that 360 degree is equivalent to one complete oscillation. This is something I just want to bring forward to you. Okay, you can basically draw this. This is so important. Right. All right, kids. Now I just want to tell you that when one oscillation is done, so we can compare this. We can say that 360 degrees during this time, you can also say a whole wavelength has been generated or a whole time period. So 360 degrees can be equivalent to 1 lambda, and it can also be equivalent to one whole time period, because 360 degree means one whole wave, and one whole wave means in terms of distance wavelength, in terms of time period. So this is a very important and crucial comparison that we got to make. Okay, please write this down, and then we'll draw waves for these.
Sir, I don't understand why is it equal to one time period.
I'll show you just in a bit, okay? See. Just write this particular comparison, please. Okay. Now let's look at the comparison, okay? I'm going to do it right on the next page. I hope you guys have copied it. If somebody has not copied it yet, they can ask me. Okay. Anyhow, so I'm going to make 3 waves. Exactly each wave beneath the other one. So in this wave, we have displacement on this side. One wave has angle theta, one wave has meters, and one wave has distance, and one wave has time in seconds. All right, now please look at this very carefully. You see, when one whole wave is generated, like 0 degree, 90, 180, 270, and 360 degrees. So if I go just down, let me just show you this way. So when 90 is created, exactly at that time, a quarter wave of the other wave is also generated, which is the distance wave, right? Let me just draw it, and I'm gonna color this. Let me just draw it with the same color, then I'm color this to show you what I mean. So like that, like this, and like that, and like this. Now let me show you this. Where did 360 go? Okay. Now see this. When a quarter wave, which is this much, is created, a quarter wavelength is also created. Do you guys understand that? Then a quarter time period is also created. Do you guys understand?
Yes.
Right. When half wave is created here, which is 180 degrees, so half wave means now half lambda is also there, as you can see the wave, and half time period is also there. Then, if you see this part, the next quarter when it goes to 270, it's the same thing as this. So 270 means 3/4 of lambda, also 3/4 of time period. And then 360 would mean 4/4, which is like one whole lambda, and then one whole time period. So this is why we can compare these together. Do you understand, Farina? They say they're happening in the same at the same time. Do you get it? All of them changing the same way.
Sir, the purple part is only 4/4.
Yeah, quarter. Purple means when a quarter wave in terms of time has been created, it has traveled a quarter distance and it has traveled 90 degrees. Do you understand like that?
Okay.
Yeah.
And for half, it's 180.
Yeah. Because you see, when you made a comparison, you said 360 degrees is equivalent to 1 lambda and one time period. So I said, if you want to know what would be half time period, right? So when half time period is there, it will be half lambda, and also half of 360 is 180 degree. Do you understand that? So you can see half is at 180.
Okay.
So you can go back and forth between any of these because all of these things are happening at the same time. All right, kids. Now, let's now see what do I mean by phase difference or phase difference. All right. So half of it we're going to complete next time, but right now we're just going to look at phase. So in fact, let's write it as a question. So a wave has been given to you in degree theta and displacement in meters. So let's look at the wave. So this wave has angles, obviously, 0, 90, 180, 270, 360, this is 450, this is 540, this is 630, and that's 720. You guys agree? Understood?
Yes.
Okay. Now I'm going to write some points. A, B, C, and F, D, and E. Now the first question is, find the phase of A, B, C, D, E, and F. We got to find the phase, okay? So as you can see, A is right here, which is at 90 degrees. What do you think is the phase of B? Anyone can find B?
270.
270. 270, it's right here. Okay, Farina.
Oh, okay.
C is 360. D is 540. E is 630. And F is 450. So phase means what is their current position right now on the wave. Understood?
So the current position, is that the definition of phase?
No, it's not the definition. It's just to explain it to you. In fact, there's no definition of phase. It is just a position, okay, at a particular angle that we're looking at. Understood? All right. So this would be all for my side, from my side. On Monday, we're going to meet again. And when we do, we're going to discuss if we're first going to discuss the worksheet. And then we're going to go forward with this wave thing. See you then.
Thank you, sir. Bye.
Bye.
Thank you, Sir Hafiz.
Allah Hafiz.